Okay, I thought I might just have a look at some questions from last year's exam. Just a few odds and ends here, just from all sections. Ones that, in the first three sections that I looked in the examiner's comments and mentioned that students had difficulty with. So let's have a look at this one. I've already helped some people in class with this one, but this one goes back to the binomial expansion. Of course, that's on the information sheet here. So there's the formula. So that's a good starting point there. Okay. We've got this power to the n thing, so we should use n in the appropriate place in the formula. And our y aspect here is -2. You can see there. So there's our y. So if we apply the formula, we start off with nc0 x to the n and then -2 to the 0. That would be the first term. The next term, if we apply the theorem, is that it's nc1 x to the n minus 1 -2 to the power of 1. Okay, now what it's asking for is find n if we know that the coefficient of x to the n minus 1 is -18. Okay, so I can see already here that I've got that term, so I don't really need to go any further. And its coefficient, remember coefficient means the number in front of the term, if you like, is going to be made up of these two things here. Okay, the nc1 and the -2 to the power of 1. Okay, so let's have a look here at that situation. And we know it's -18. So if I now go back to these two here, that means that nc1, so that again, nc1 times -2 to the power of 1, which is -2, has to equal -18. Okay, because that's the coefficient. Those two there, as I said, those two multiplied together will be the coefficient of x to the power of n minus 1. So that means that nc1 equals -18 divided by -2 is 9. Now, when you look at the Pascal's triangle, I'll just draw it up here a little bit. 2, 1, 1, 3, 3, 1, 1, 4, 1, 5, etc. All these ones here, if I just get the yellow pen back again, all these ones here, that second diagonal grouping, are all the C1s. So that's 2C1, 3C1, 4C1, 5C1. So, for example, 4C1 equals 4. 5C1 equals 5. 6C1 equals 6. So, we've got nc1 equaling 9. That would mean, based on that pattern, that n equals 9. And that's the answer. We'll have a look at this question next. Express e to the power of 14 in terms of x and y. Now we've got e cubed and we've got e to the power of 4, and somehow out of that we've got to get e to the power of 14. Okay, sort of, obviously there's a little bit of lateral thinking that goes into this, but I can sort of think here that if I had e to the power of 3 squared, that would be e to the power of 6, and if I multiplied that by e to the power of 4 squared, that would be e to the power of 8. So e to the power of 6 times e to the power of 8, that would be e to the power of 14. So in terms of x and y, remember e to the power of 3 is x, so I've got x squared times y squared. So e to the power of 14 in terms of x and y would be x squared y squared. Now we need a simplified expression for the square root of y plus log log x there, or log x to the base c, ln x. All right, so let's do our substitutions here. So we've got Square root of e to the power of 4 plus, and you know I like to use log base e, we've got x is e to the power of 3. All right, so now there's a rule here that says if you've got log e, the base e, and the number there, that just becomes the number. But if you forgot that rule, you can get that anyway. I'll do the second part first because you can make that if you wanted to. You know how to bring that 3 out the front, and that would be 3 times 1, which is plus 3. As I said, you probably don't need that step if you recognise that rule anyway. And over here, the square root of e to the power of 4 would be e squared. Okay, so e squared plus 3 would be that. So there's a couple of questions from the first part of the exam. I'll come back in a minute and do some trig questions. Okay, with this next one, you might remember a whole heap of rules that were called complementary angle rules. And they sort of must be a bit of a light bulb here when you've got sine equaling cos, that sort of relationship. One of the rules we looked at, and well, first of all, what quadrant are we in here? We're in the second quadrant. And because I've got 15 and 30, it might be just worth converting that sine 11 pi on 15. I'm going to convert it to 22 pi on 30. Okay. Now that then, because we've got sine and cos, we're in the second quadrant. The second quadrant rule that we talked about in class for complementary angle rules is that sine pi on 2 plus theta equals cosine theta. Now the way to develop that rule is that we're in second quadrant and the sine SIGN of the right-hand side here is at the mercy of the left-hand side ratio. So we're in second quadrant. Sine is positive in second quadrant, so the cosine here will also be positive. So now it's a matter of saying, okay, well, pi on 2, remember, will be the same as 15 pi on 30. Right? So here I can say that sine 15 pi on 30, that's pi on 2, plus 22 minus 15 is 7 pi on 30. Okay, so there's my rule here. That's going to be the equivalent of, because that's my theta, that's 7 pi on 30, that's going to be the equivalent of cosine 7 pi on 30. Okay, so by applying the complementary angle relationships, you can develop that rule from there. This one here's an interesting question. And these in this format aren't too common in exams, but might come up again. Use a rectangular grid and appropriate triangles to estimate the values for sine 7 pi on 9. So let's count our way around. Now, what they've done here is they've divided the unit circle into divisions of 9, pi on 9 that is. So pi on 9, 2 pi on 9, etc. So 7 pi on 9 is going to be that one there. Okay, now remember the sine value for that is that horizontal component, all right? And if we read down to see what that horizontal component is, we'll draw a straight line down there. That's not very straight, just don't do that. Looks to me very much like it's 0.65, is it? It's like 0.75. Oh, beg your pardon, I've gone the wrong way. Start again. Okay, the sine component here is not the horizontal one, it's the vertical one. So there we go, it's that one there. So that's 0.65. That distance from the middle, so sorry about that, the sine component, I'll write it out now because I mucked it up. It's going to be, the sine component is the vertical component, not the horizontal, that's the cosine. So that sine theta there is 0.65. Okay, so sine 7 pi on 9 equals 0.65. Now it wants tan 15 pi on 9, so that's 8, 9, 10, 11, 12, 13, 14, 15 pi on 9 is around there. Do this in green. So it's that one there. This time it wants tan 15 pi on 9. To get that, we're going to have to get two values, the sine of 15 pi on 9 and the cosine of 15 pi on 9, and then divide them. So let's look at that. Tan 15 pi on 9 equals sine 15 pi on 9 divided by cosine 15 pi on 9. So sine 15 pi on 9, once again, is this vertical component. So it's going to go down to about there. Might just use a straight line for that. Here we go. Down to about there. And the cosine across that way. Okay, so sine 15 pi on 9, if you read that distance down there, is going to be 0.85. And because it's in the negative direction, it's actually going to be negative 0.85. So negative 0.85. The cosine component is positive, and it looks at about 0.5 there. Okay. Now, cancelling that down is not all that easy. You might want to convert those to whole numbers by multiplying by 10. Might make it easier. You can do that. Okay. And if you do that, you get negative 1.7. Remember what I said in our revision about you need to still have sound mathematical computational skills, things like negative 8.5 divided by 5. All right, when I come back in a moment, I'm going to do a couple of differential calculus questions, starting with that one. Okay, so the final couple of questions in this video involve question 12, which was a really difficult question, I thought, in the non-calculator section last year, and involves a change of base theorem. And that crops up every now and then, okay? And sometimes you need to realise that it's actually on your information sheet. If I can find that. Here it is. Okay, so where is it? There it is. It's actually not labelled change of base theorem, so just be warned. So that little theorem there that under the log laws heading, and you can see it's called the change of base theorem because you can change any log to a different base by applying that rule. Okay, so let's apply that rule in this situation. We've got, because what we've got here is a situation where we've got our derivative in log base e, and we've got the original equation log base 2. So it would make sense straight away to change that to a base e, that g of x to a base e, using the change of base theorem. So to do that, it becomes this over log 2 to the base e. Okay, so you put the new base there, and on top goes the x, and on the bottom goes the 2. So we've now done that. Now the tricky little thing here is then to make that separate that out to this 1 over log 2 to the base e times log x to the base e. Now remembering, and this is what, according to the examiner's comments, that caught a lot of people out, is that that's actually a number. All right, 1 over log 2 to the base e is a constant, is a number. Okay, so when we get g dash x now, okay, it's in fact, it's just like, if our g of x, and I'll get rid of this in a second, was 3 log x base e, the derivative of that is just 3 times 1 over x equals 3 over x. Okay, so with this one, it's a similar sort of thing. because we've got a number in front of the log x base e, that number stays out there. So we go g dash x equals the number 1 over log 2 to the base e, and times the derivative of the log expression, which is just 1 over x. Now you can see, and I'll put it back to ln form now, g dash x equals 1 over x times log 2 to the base e, so x ln 2, which we were asked to find. So a key step here, I can't emphasise enough, 2 steps. First of all, executing the change of base theorem and recognising what it is and that it's on the formula sheet. Secondly, that little separation there. Okay, otherwise you can start doing quotient rules and all sorts of funny things. But just that separation out there. Okay, it would be the same separation as if you had, and I'll go back to what I was talking about before. If you'd have had that, okay, that would be the same strategy. It'd be 1/3 times log x to the base e. Right, so that's question 12, or 12a in fact. So the next question builds on that. Okay, so the function f of x equals the square root of x is the same gradient as g of x log x to the base 2 for only one x value. Determine its gradient. So that means here we've got to make f dash of x, if they've got the same gradient, and I'll just go back to a darker pen. If it's got the same gradient, that means that f dash of x will equal g dash of x. Okay. Now, f dash x, okay, so we've got the square root of x. So I'll just go over that again. The f of x is x to the half. So f dash x there will equal 1 over 2 x to the negative a half, which is 1 over 2 root x. Okay, so that's the derivative there. So g of x, as we know, is log x to the base 2. We now know from the previous question that its derivative, okay, is 1 over x log 2 to the base e. Okay, that's from the previous question. So its g of x equals 1 over x times ln 2, and I like to do the base e bit. There we go. So that's the first thing to establish. That means then if the gradients are the same gradient, that means you've got to make those two equal each other. So 1 over 2 root x equals 1 over x log 2 to the base e. Right, now, because they're both denominators there, and 1 over, that means that we just have to equate the denominators. That means that 2 root x will equal x log 2 to the base e. All right, so what we can do now is divide both sides by 2 and divide both sides by x simultaneously. Divide both sides by root x and divide both sides by log 2 to the base e simultaneously. Okay, so that will get us to this. We'll get 2 over log 2 to the base e equals x over the square root of x. Okay, so I've divided both sides by root x, both sides by log 2 to the base e. In fact, it's almost undoing it. I've showed you before that cross multiply theorem this year, and it's almost undoing that. Okay, it's going back the other way. So now, from there, and I'm just going to go up to the right hand side here now. That means that 2 over log 2 to the base e. Now, x divided by square root of x, and this is something that sometimes people overlook, It's like 2 over square root 2. 2 over square root 2 is square root 2 because root 2 times root 2 is 2. Okay, so if you get x over square root x, that's actually going to be square root of x. All right, we're getting there. Now, to find x, we've got to square both sides. Okay, so if we square both sides, that means 4 over log 2 to the base e squared equals x. Right, so there's our x value. Now we have to find its gradient. All right, so that's the x value that we've got. Now to actually find the gradient, you have to put the x value into the derivative. Okay, so a little bit of tricky stuff here. So g dash x, you can see it beside here, next to where I'm writing. There it is. Okay, so I'm now going to substitute that value into there. Okay, and we'll see if we can get our final answer, our gradient. In fact, I'm actually going to, I'm just looking at it here, I'm actually going to put it into the f dash x, beg your pardon. So let's just undo a bit here. So I'm actually going to put it into the f dash x. Doesn't matter because the gradients are the same. So f dash x equals 1 over 2 root x. Okay, so f dash x equals 1 over 2 square root 4 over log 2 to the base e squared. Extend that square root a bit. Okay. Now, obviously, if we're square rooting that situation there, sorry, beg your pardon, I'm not squaring the 4, am I? Let's just go back a step. I'm only squaring, might get rid of that bracket and that bracket. I'm only squaring the denominator, which is there. Okay, so f dash x equals 1 over, so we've got 2 times, the square root of 4 is going to be 2, and the square root of log 2 to the base e squared is just log 2 to the base e. That gives me 1 over 4 over log 2 to the base e. Okay, 2 2's are 4 there. Flip it up the other way, because 1 over something, you invert it. So we get log 2 to the base e over 4. And that's the gradient. Pretty involved question. Sorry for those couple of blunders along the way there, but we got there in the end. I hope that helps, and we'll do some more questions coming up soon.